Good morning, everyone. So a great pleasure to have you today in this big room. Welcome Professor Mariangeles Serrano from Barcelona. She'll speak us about renormalization of complex networks in latent space. And this is special because we are now downstairs, offering upstairs. So, Julia, do you want to say something? Or?
Sure. Well, welcome everybody. Sorry, I'm Julia Altman. That was not what I expected, but I'm happy to do that. Yeah, there's a lot of new faces, and maybe thank you for giving me I won't take much of your space, I promise. Some of you may or may not have been at ES upstairs, but not downstairs. Some of you may have not been. So welcome again. This is the Institute for Advanced Study of the University of Amsterdam, still the one and only university-based ES in the Netherlands. And of course, every Thursday we have the Dutch Institute for Emergent Phenomena here, which is one of our most inspiring, we believe, interdisciplinary communities to convene. And we're specifically thankful to you to put all this effort into getting a wonderful speaker today, which I know was very challenging to make happen. So on behalf of also the director of the I'd like to just warmly welcome you. And there is lots of people in the audience that may or may not, be specialized in the topic. So we'll see. We're very excited about that.
I try to make it accessible.
Exactly. Well, it includes me, by the way, right? It includes me. But I would encourage you to also over lunch talk to, for example, our journalist in residence who's in the audience, our artist in residence who's in the audience. So it's a very mixed, lovely community of people who's excited as I am too.
Thank you very much. Well, thank you very much for the invitation. I'm really, really glad to be here. I'm going to talk about renormalization of complex networks in latent space, but I'm not going deep into the technical details. I just want you to convey the very general idea of what we are doing, and why is this so difficult. So my field of research is network science. We study networks, which are basically graph representations of complex systems. By the way, stop me at any time. Ask questions if you need. So we have complex systems with discrete units, and we represent them as graphs, these kind of structures here. You know that networks are everywhere, from biology, economics, society at all levels. And what is interesting is that all those networks, all those graph representations of complex systems share a number of common universal features. This is what makes networks so interesting. We can distinguish between conditions and emerging properties, although I don't like that much this kind of distinction. Sometimes it's not that easy to say whether a property is a condition or whether a property is an emergent feature, okay? But we can say that, for instance, conditions that make networks as they are is numerosity, and networks are made of a large number of elements. Large number, and sometimes people in biology let's say a network of 3 nodes. No, this is not a complex network from our point of view. Okay, so we need large number of elements interacting. There is typically no central control. Our systems are out of equilibrium, heterogeneous. There are feedback loops, long-range interactions, and as a result, we get emergent behavior, right? Like the name of your institute. That is so amazing. So what kind of emergent properties we study? Self-organization, structures which are between order and disorder, because these are not lattices. You see, these lattices, very well organized, very regular. We don't study lattices. And we don't study trees. These are different from lattices, these are different from trees, but they're not completely disordered either. So there are structures between order and disorder, and display properties like modularity. There are communities there, regions which are more interconnected inside as compared to outside. There are nested nets, so hierarchical structure. At the same time, networks are robust and vulnerable, which is very two sides of the same coin, very interesting. Non-linear behavior, memory adaptive behavior. But as I was saying before, it's not that clear sometimes to say what is a condition and what is an emergent behavior. Non-linearity, for instance. Non-linearity should be here or here. So somehow my philosophical approach to this is that we make this distinction a little bit artificially, But anyway, let's keep in mind that these representations of complex systems, these graphs, somehow have these properties attached to them. Huh? In this talk, I'm going to talk about the more basic representation of a complex network, which is this kind of graph here. All the nodes are the same, right? Except for the fact that some have many connections, for instance here, and some nodes have just a few connections there. Like for instance, this one, okay? And all the links are the same as well. So there are no a directionality associated with the link or an intensity associated with the link. So this is a very, how to say, very simple representation of a network. Real networks are not like this. Real networks, we have directions in the links, weights, different kind of nodes, multiple scales, and so on and so forth. Huh? But for the moment, let's stay with this kind of representation, very simple. In this talk, I'm just going to tell you something about the structure of networks. I'm not going to talk about dynamical processes or anything like that. Yeah? Just the structure of networks. And I'm going to focus on a number of properties which are very basic and very simple that refer to the structure of networks. One is sparsity. Real networks are sparse. What does it mean? That the average number of connections per node is very low. Yeah? So imagine we have, for instance, a network representing the internet at the autonomous system level. You may have there 30,000 nodes, but the average number of connections per node is 6, 10, 12. This number is typically very low. When we talk about models, we can be more rigorous, mathematically speaking. But for the moment, just keep in mind this thing, that the average number of connections per element is very low. Then other properties is this small world property. Do you know about this? Yeah? So every pair of nodes in the system is very close to each other. I'm going to tell you a little bit more later. Yeah, but keep this thing into mind. That is basically that everything is very close to everything else in this kind of structure. Hubs and the distribution, which is scale-free or power law. Yeah? So if we count the number of connections per element in your system, this has 1, this has 3, this has whatever. We can plot a distribution. And typically, in many real networks, what we find is that this distribution, this is in log scale, is similar to a power law distribution. So that means that in this log scale, it looks like a straight line, meaning that there are very few nodes, which are very large degree, highly connected to the rest, like hubs, like in the airport network, there are hubs there, right? While most of the nodes are very low connected. Yeah? So the probability that nodes have low number of connections is very high. But you have everything in between. It's not bimodal, you have everything in between. Yeah? But typically in many systems, you have this power law distribution of the degrees. I don't care whether it's a pure mathematical power law or not. What is my interest is that this is like a broad distribution of values. You know, it's hereditary. Yeah? And clustering. Clustering, this is very important in this talk. Clustering is the happening of triangles in the topology. Looks very, very simple idea, right? They have triangles. Yes, triangles are everywhere. No? So triangles are here in this kind of structure, and these triangles are coalescent. They share edges, right? This is what happens in real networks. You don't have one triangle here, one triangle there. No, all triangles coalesce. They share links. Yeah? And this is very important property. Seems very simple, but it's very important. This is talking about correlations between the degrees of the nodes, right? So let's focus on this set of structural features associated to these very simple representations of complex networks. Now, what kind of question, big question, are we asking about these complex networks that we characterize looking into that set of properties? So there are few very big questions that we can ask, right? One is about dimensions, which is the dimensionality of such a structure. It's not the topic of today. We have other questions about features, about whatever. But let's focus on this, on the problem of scales. If I take this structure that is representing this complex system, and I change the length scale at which I observe this system, I zoom out, let's say, I have my network, I zoom out on this structure, what do I see? Can I do this operation? How do I do this operation? And what do I see when I do this? Yeah, this is not super clear because when we work with real networks many times, we just have single snapshots. We don't have the network at different scales. We have the internet network at the autonomous systems level. We work with this. We have a social network between people. This is single scale, right? So in many cases, we have data for single scale networks, but okay, what happens when we do this? No? Can we do this? This is the first question. Can we do this? Can we try to think about a method to change the length scale in a complex network? And what do I say? This is the question. And this is my talk. Yeah? I'm going to tell you about what happens when we take this complex network. We apply the machinery that we call the geometric renormalization technique. Yeah? Zoom out and zoom in. Okay, this is the second part. But for the moment, to zoom out on the structure of real networks, and what's the result? What do we see? Okay, let's start. The first thing that we have to care is about how to define lengths, distances on networks. Because to define length scales, I need to be able to have a good definition of distance, of length in my system. Now, if I have this representation of a complex network, which is a topological representation, what does it mean, a topological representation? Is that you have these nodes connected by links. If I take this node here and put it here, but I don't cut the connection, okay, the connection is still there, I'm not changing this structure. This structure does not change. Yeah? So this is kind of topological representation. How can I count distances in this topological representation? For instance, by counting the number of links that I need to travel to go from one node to another. In this case, the distance between this and this is 2, right? Because I need to go, the minimum number of links that I need to travel is 2. 1 and 2. Okay, very easy. Do you agree? Is it easy? Super easy. Yeah? This is called the shortest path length. This is the shortest path length on the topology of the network. And it's very easy. Now I take all the nodes and I compute all the shortest path lengths between all person nodes. It's computationally costly, but it's very easy, right? And then I have a distance associated with the system, which is very easy to understand, easy to compute, even if it's costly, but it's easy to compute. And it's a metric distance. From the mathematical point of view, it's a well-defined metric distance, so it seems to have all the right properties. But there is a problem with this metric. There is a problem. And the problem is that when you compute the distribution of shortest path lengths on real networks, this is what you find. This is what you find. That the distribution of shortest path length is very peak, is a peak distribution around some small value. That means that most, for instance, this is for the internet, this is for Facebook, this is for friendship, people following others on Facebook, okay? And what you see here is that in this network you have millions of users, but the average of the shortest path length is around 3.57, maximum 4.5 here. Yeah, but doesn't mean that the distribution of shortest path lengths is very homogeneous and very peak around a very small value. And what does it mean then? That everybody is very close to everybody else in terms of the shortest path distance. Yeah? You don't have a wide range of length scales in your system that is able to separate the different components. Everybody is more or less at distance 3. In a system of millions of nodes. Yeah? Or in this case, thousands of nodes, and the distance again is 3, 4, whatever. Imagine that you have to plot a map with these distances. Everything is going to be cluttered together, more or less. You are not going to be able to use this map for anything. Yeah? So,
can I ask?
Yeah, sure.
Is this comparable, like, for example, with the distribution of IQ? Where everything is around hundreds and most people are around hundreds?
Well, I mean,
Or
in that case, I don't know about that distribution, maybe that distribution is Gaussian. This is not perfectly Gaussian, but anyway, it's yes. Common, there is a peak distribution. Yeah, you don't have a fat tail
Yeah.
of values there, you know? It's peak distribution and around a small value.
Mhm.
Okay, so that means that this distance is mathematically well defined, easy to compute, is meaningful, but it's not useful to separate parts of the system. So we have to do something else. We cannot define length scales based on that. Yeah? Let's try another way. Another way is, okay, very easy. I plot I throw my nodes on a metric space or Euclidean plane, whatever, right? I can throw the points and then I connect every pair depending on their distance. The closer they are, the higher the chance that they get connected. This is very easy, right? And then this has the advantage that I already have a metric space, Euclidean space, for instance, and in which I can define length scales. No, is our typical way in physics, for instance, to do things. And then another advantage is that there are real systems with a kind of explicit geometry associated, like the brain, no, our brain, which is in 3D Euclidean space, or airport network, train networks in geography. So that will solve the problem. No, we already have a space, we can define lengths and look at the things and so on and so forth. Okay, this is not the solution either. Why? Because several problems. The first is that not all complex networks have an explicit metric space associated to it. Yeah, that's the first. So in the cases in which we don't have this explicit space, what can we do? The second, yes.
What does it mean? What is an explicit metric space?
Explicit in the sense that you can recognize it right away. So you look at the
Graph is a set of lines connected with the cement.
yeah, but I mean the graph is a mathematical object that represents a physical system, right? Or a real system.
Is explicit mean like physical? Yeah.
Is what?
Is extracted from data.
Yeah.
Okay.
So we think about the airport network. You have geographical locations, so you can find a geographic distance between them, right?
Okay, from here it's extracted from what go away.
Yeah, I mean,
Explicit.
no, explicit means that you can measure. Explicit means for me that you can measure this space. So in here you can measure the distance in kilometers.
Spatial data.
Spatial.
For Facebook, there would be no.
Yes. In Facebook, you can think about, okay, this people is located in this city, that person is located in that other city. This defines this already defines a distance, right? But the problem is that typically the distance, this kind of distance, is not the only factor that contributes to the formation of links in a network.
So like Facebook, the topology is very natural, but the geometry not so natural.
Not so natural. So I'm pretty sure that maybe there is a component of the geographical distance between users that may have a role, but it's not the only information that has an impact on the formation of links. Yeah, and that's the main point. Even if you have this kind of system in which there is a spatial distance that you can measure that is very obvious associated to the system, typically it's not the only factor that affects the formation of links. It's not even in the brain. Not even in our brain, the distance that this region is here and this region is here is not the whole story. This distance is not the whole story.
So whenever we have network, we also have a system that this network represents.
Yes, it might.
It's a part of definition of a network, or a network is like abstract of the system.
That's a very good question. The thing is, you can study graph theory in mathematics, and then you don't care about real systems. You do graph theory, right? And you compute, I don't know, you can compute many things that we compute as well, right? We use graph theory, spectral analysis. You can do many things disconnected from the real world. But in my case, my interest is about reality, is about the real world. So I use this graph representation to understand a complex system. Yeah. for the moment, here I'm going to talk about commonalities across many real systems. So this is my focus. So that's why I'm going to talk about the sparse network. Why? Because real networks are sparse. About networks which are small. Why? Because real networks are small worlds, and so on and so forth. So we recognize that real networks have these properties, and we study this from the point of view of graphs. But for me, at the end, I want to use networks and graphs to understand complex systems in reality.
Okay, so does it mean that whenever you define a network, this means that the system is also explicitly stated that this network is a graph of the system?
Typically, this is our inspiration, right? But once we recognize that there are a certain number of properties which are common, we can try to think about models that replicate these properties independently of the system, of the specific system. So at the end, I'm going to introduce a model which replicates networks which are sparse, small wall, with clustering, with scale-free distributions, and so on, and not necessarily attached to any specific real system. You know? It's a kind of representation of, but what is important to us is that these networks mimic these properties of real system. So I'm not going to talk about dense graphs because real networks are not dense. There are a few, but okay. The ones that I'm talking about, the most real complex networks are not dense. You know, it's this kind of thing. Anyway, let's go ahead. So the problem is that not all networks have this explicit space that you can measure. Even if they have the explicit space, this distance is not the only factor that explains the connectivity. And there is another one, which is very important, is the fact that even if you are able to overcome these two problems, the thing is that if you use this probability of connection here, depending on distance, you only get short-range connectivity. And real networks have also long-range connections. That means that you need like two different connectivity loads to replicate short-range connections on one side and long-range connections on the other side. You know? And this is not relevant to have these two connectivity loads. We want to have one connectivity load for connections at all length scales, at all ranges. Yeah? So, which is our solution to this problem? This is our solution to the problem. So we have a latent metric space where nodes have certain positions, and nodes connect with some probability of connection, the same for long and short range connections, that at the end produces networks that mimic the networks that we observe in the real world. Yeah? So networks live in some underlying hidden metric space. So we have this representation in the metric space plus a connectivity law, a probability of connection that is producing these connections at all ranges, all length scales. Yeah, well, this is basically the distance. So for the brain, this is not the 3D Euclidean space, the anatomical embedding. For the airports network, this is not geography. Okay, some latent space that is able to mimic the structure of the network with a single connectivity law.
Can I ask you a
Yes,
philosophical
sure.
question?
Sure.
You start out by saying networks have a small world property. I mean, if that's the case, then your whole approach, like trying to scale and renormalize, falls apart. Now you're going to introduce a kind of like latent space to make your renormalization work. Is that not like, you know, trying to find a solution for a problem that's not there? Because it's kind of like, you start out by saying networks are a small world. Isn't then the answer renormalization is impossible because we have a single landscape?
I mean, you went to the core. This is the most important question in this kind of work. You are completely right. So, how to combine a small wall on the one hand, this long-range connection there, with the hierarchical structure on the other hand? This is the difficult thing here. That's why we need some special kind of geometry, as you will see. And then how to do renormalization there? Because this is curious everything. And we're starting to understand more or less the way in which we have to go, starting to understand, but this is going to be a long-term kind of project that is just starting now. Yes, and this is the question, The thing is, I mean, I'm going to talk here about renormalization of the structure of networks. I'm not going to talk about renormalization of dynamical processes or anything which makes this very different from physics, because in physics, we don't care about renormalization of a space. It's trivial, right? Renormalization of a space in physics is trivial. So these boxes that go into the large box, that we rescale into the small box, I mean, Euclidean space is so similar to itself. So it's not a problem. What we care in physics is about Hamiltonians and the physical process that is going there. This is one step before.
One question, may I comment to your questions? Maybe the small world property is a topological property, and then what you address is geometric property. So topology versus, is it topology versus geometry?
No, it is together.
Together,
The things are,
yeah.
the things are, as you will see, the things are together. And we managed to find a way in which we can renormalize, rescale, whatever. The structure. But I'm talking about the structure. It's like in physics. What happens in physics instead of a lattice? There is no lattice anymore. You have the lattice and a double range connection. How do you have to renormalize the space that supports the process? You know? So this is very difficult.
Is your in physics, but so if you do a block spin in ICMO or something, you also renormalize the lattice, but then also the dynamics on top of the lattice. Is that your goal eventually to go there with complex networks?
Yes, in a few slides.
Yeah, this is probably, I don't know, a very basic question, but what do you mean by renormalization?
I mean, this is a kind of techniques. In physics, we have a set of techniques to try to change the scale at which we observe a physical system. So what happens if we observe my system from this? They change the length scale at which we, and then try to understand what is going on there.
So the zooming in and out?
The zooming in,
that's
yes, the zooming out, that's renormalization in physics. And then the idea is that we cannot take those tools and apply them to networks right away, because these networks are small walls with hierarchical structure. So to combine the two things, it's difficult. Finite scales is difficult. And then first we have to solve this, to try to inspire ourselves into the methods that we know from physics to try to do this operation. Okay? Yeah. But first, I need to talk about this network geometry, this description, because it's the way in which we introduce the length scales, the distance, how to measure the distance, such that then we can apply this of ideas. Yeah? Okay, so this is our proposal. Let me be a little bit more specific, because that image was very general, right? So we have a family of models that we call the SD model. Sphere in D dimensions. In here, I'm going to talk about one dimension, S1, a sphere in one dimension, so the circle. Yeah? But then we have the formulation for D dimensions in general. This is a very simple model that allows us to do this thing of putting together in the same model the small world property and the hierarchical structure of networks. Yeah? And we do this in a very simple way. You have this space, this is a circle, this is standard space, right? A circle in which we draw nodes in our model at random there. Every node has a certain a property, but that we call popularity, of importance, of mass, how attractive is the node for others. And since they are in this space, we can define distances in this space between pairs of nodes, right? Then we connect every pair of nodes with a connection probability. It's one single connection probability that depends on the distances between pairs of nodes in this circle and these masses, if you want, this popularity of nodes. Think about a mass here. This can be a mass. So that this is a kind of gravity law, right? This is a gravity law. So the larger are the masses, the larger is the probability that the two nodes get connected. And the shorter is the distance, then the larger the probability that the nodes are connected. It's a gravity law. This parameter controls the level of clustering. Do you remember triangles in your system? Why is this important in this picture? Because at the end, clustering at the level of the topology is just a reflection of the triangle inequality happening in the underlying metric space. So in the underlying metric space, we have the triangle inequality, which at the end translates into clustering at the level of the topology. And this parameter controls this coupling between the topology and the metric space. And with this other parameter, you control the other degree. Doesn't matter. So the number of parameters in the model is very low, right? Very simple. Gravity law model, and you connect the things and so on. And this model, which is so simple, is very rich. It's super. It's very interesting. It's a maximum entropy model. Yeah, it's a maximum entropy model, which is able to produce structures that mimic networks in the real world. Are sparse, are small wall. If this distribution of hidden degrees of masses is scale-free, then you get a distribution of degrees in the network, which is also scale-free, and with high levels of clustering and more properties. You know? Yes.
Could you explain this distance function? Because I think distance is just the arc length, but it's not. In this case, it's something like delta. And this n over 2. So what is this n?
Well, this is sorry. This is my fault. This is this is the linear distance, right? Because this is something I didn't say that the density of nodes is 1 in the circle. So the radius is adjusted such that the density of nodes in the circle is always 1. For convenience. Yeah. So this is R. This is okay, a little bit confusing the notation, but this is the radius.
Okay,
yeah. The thing is, with this very simple model, we are able to reproduce all the features that we were trying to reproduce.
But you do so by introducing a geometric
Yes.
space.
A latent
Which you
space.
just in the previous slide said, well, that doesn't solve our problem now. You introduce nonetheless a geometric
Yeah,
space.
but it's different because here we have the second variable.
So you combine it actually.
Yes, and you will see the result of combining the two together. So this is that the distance is not an, but there is an effective distance. What is the effective distance? This thing here, the two together, the distance over the circle plus the effect of the masses. The two things together is what is the effective distance. You know? Yeah. And the model has many properties which are interesting, but let's go ahead with this thing. Using the model, you can produce different degree distributions. You can produce scale-free degree distributions with different values for the exponent, different levels of clusterings, and so on. But in any case, you have a small world property, heterogeneous degree distributions, high levels of clustering. You can the average degree, you can reproduce symmetries that we observe in networks. I don't have time to talk about this, but anyway, it's a very simple model, very powerful to reproduce the properties that we observe in real networks.
All the 3 parameters are, let's say, the dimensionality of the sphere.
Yes.
The
Beta for the level of clustering the triangles, the coupling between the topology and the metric space.
And then the mass distribution also.
Yes, the mass distribution, and this mu for the average degree. Yes.
Is there any interpretation for the power law, like for the exponents that you get, or is to?
Well, typically real networks have an exponent. If you go and measure real networks, it's not clear power law, more or less. It's close to a power law with an exponent between 2 and 3. This happens. The brain is different. The connecton of the brain is typically above 3 point something. But many networks are between 2 and 3. You know? But in this model, you don't need to be confined between 2 and 3. You can use 4, 5, whatever, even another kind of distribution that is not power law. You know, it's very flexible in this sense. And the very interesting thing is that this model, the S1 model, can be mapped to a purely geometric model in hyperbolic space. Yeah, you take the mass, the size of the knot here, and you do this transformation, this logarithmic transformation here, such that nodes which have larger masses are closer to the center of the disk. Yeah, so you have low mass, you are closer to the periphery. You have high mass, you become closer to the center. Yeah, if you do this operation and then you go to the probability of connection and transform it with this, then you get this, which is a model that only depends on the distances between nodes in this space, and this starts to be hyperbolic distance in the plane. Okay, so there is this isomorphism between the S1 model, we call the S1 model, and the H2 model. So it's a model in the hyperbolic plane in which nodes are connected just depending on the hyperbolic distance between them. Right? And I like to talk about this Newtonian or gravity model. Well, this is for me kind of Einsteinian, right? Because this is only space. It's only space, no masses anymore here. Just a space, and they're connected based on distance. But the geometry is different. The geometry is hyperbolic geometry. You know, it's this kind of geometry in which, as you go far from the center, you have more and more and more space. And it's a natural geometry to embed trees, right? Hyperbolic space is the natural geometry to embed trees. And since we know that networks are hierarchical, you can think about networks as trees with cycles, trees with triangles, right? So somehow it's a natural space that is able to incorporate the hierarchical networks. And it's the space as well that explains that the combination between the small world property and the hierarchical structure.
Yeah. So in the right-hand graph, you say that points closer to the center have a higher mass. That's how they.
In this mapping, yes.
Yeah, in that mapping. So what about the radius, where they are in the rotational position? How is that defined? Is that
the same? You keep the same angular position as in the S1, and you just change the radial position according to this logarithm transformation. The only thing that you can. And then this becomes this kind of model, which is just geometric in hyperbolic. This is very nice, because this allows us to go from here to here anytime. So this is very convenient to do calculations. It's more convenient with two contributions which are separated. While this is very convenient to do visualization, to do operations like navigate the map, right? Navigate, we can do navigation, we do routing here, and so on. So depending on the task that we want to do, we stay here or we stay here. Okay?
And when it comes to the normalization?
This is the minimum set of concepts that you need to make progress into, because otherwise it's going to be impossible to understand. Yes.
Can you explain a little bit more the hierarchical structure? And
because you have this distribution of degrees, right? I mean, hierarchical structure manifests in different ways. One way is that the distribution of degrees is not with a large number of neighbors and not with a low number of neighbors there. There are other ways in which you can see this hierarchical structure, like nested nets. You have structures inside the structures inside the structure. You know? Yeah.
And do you introduce that through your distribution of your row K, so your
Yes.
mass distribution?
Yes,
And
the mass
basically
distribution.
somehow that generates the.
The distribution. Yes, you're right. So let's make progress. You can use the model to reproduce the structure of the network. You can go this way from the model to reproduce the topology that you observe in real networks, or you can go the other way around, right? you can take a real network and to try to find the coordinates of the nodes in this underlying metric space. You can try to do this inference of the coordinates of nodes in the metric space. For this, we already have the tools. What we do is basically what we apply kind of machine learning to guess an initial condition, which is convenient, and then we do maximum likelihood optimization, such that we are able to find the coordinates of the nodes in the, doesn't matter, S1 or H2, doesn't matter, the kappa and the theta, for each node in this metric space, and then we do some kind of validation that what we are doing is well done. And we find this kind of maps. This is one of the maps that we find for world airports. And what I wanted to show here is a few things. First thing is that in the model, in your model, all the nodes are distributed at random, right? Uniformly at random in the circle, the angular coordinate. But when you do this mapping of real networks, this is different. You see these void regions here. So this is denoting like geometric communities there. This is related to the happening of communities in networks. And then what I did here is to plot different airports with different colors depending on the continent. And this is information that was not given to the embedding tool. This is the only thing that we passed to the embedding tool was the structure of the network. But we get this right that
Which network did you start from?
the world airport. So this
World Airport, sorry.
so numbers, these numbers.
Is it measuring the distance between those 2 points?
Sorry.
Is the distance between 2 points in this network?
So this distance is the distance.
No, so you said I gave the graph of all the airports. So this is connected. Airport 1 is connected to airport 2, but is there also the length of distance between those? Oh, that one is not.
It's not provided, just the topology. Airport 1 is connected to airport 3.
And the connection is only if there is a flight between airport.
Yes, there are
and
flights between them.
Okay.
So airport 7 is connected to airport 200. That's all. We don't provide anything else. And then naturally, we do this embedding and we get these results. So what does it mean? That the embedding is meaningful, right? The embedding is able to recover information that is somehow, it's not magic, it's somehow containing the structure of the network, right? But the embedding is able to bring it out.
So the number of flights between 2 places is not part of the starting.
No, not the distance, not the number of flights, just this is connected to this is connected to that.
But not to be very cynical, I can just say I take my map of the world and then look at places that are close together, and I would also get this graph. Or
Maybe, but the thing here is that we only need the topology. And we are able to get this. That means that somehow the topology is encoding this information.
For systems where the information is hidden, you claim then this is good.
Yes,
Yeah.
so
That's trivial.
sorry.
Yeah.
For breaks,
Yeah.
that's trivial.
Yeah,
We have
okay,
them to push.
Yeah.
Yeah.
So if you do this for the larger sphere, like the 2-sphere, 3-sphere, do you really see a clear separation, or does it just fail?
If you have more features that to do hyperspheres, you need more features. How do?
So it depends on the system. So there are systems for which dimension 1 is enough. So here dimension 1 is clearly enough. We can separate the different continents right away. I mean, they are mixed together, right? So this for what in this case, 1 dimension is fine. For other systems, dimension 1 is not enough. And then you would see all the colors like mixed. And sometimes if you go to more dimensions, you get a more clear separation. It depends on the system. It depends on the system.
And I can see why it's so expensive to fly to Brazil now.
But can we really separate continents here? I see 2 continents on this picture.
America and Eurasia.
Yeah, but
Yeah.
I mean, you don't see a separation
Yeah.
between this green and this.
No, I don't.
No?
No,
No,
it's
they connect.
Yeah, it's
No, they connect, but I mean, okay. When I say a separation, I mean that they concentrate on specific angular regions of the
Yes, but if I don't
systems.
know continents, then I only see two. That's what,
If you,
what I
if
said.
you plot the continents, which is some kind of extra information, you will see everything connected, yeah? But what you can do here is to apply, this is another topic, is to apply techniques to recognize geometric communities. If you do this, you recognize the communities, but you have to apply some extra technique, let's say.
Yeah.
This is just to tell you that the embedding is meaningful.
Yeah.
It's meaningful.
Just maybe to comment, like I live in South America 30 years. It's very hard to separate the airport network because of Panama. Like every city flies to Panama.
Yeah.
Then it's one single cluster. It's already nice that South America is one connected angular region. Yeah.
But still, there are methods to.
Yeah, I don't know if you try harder with more variables or higher dimension, you could separate more, or you think this is
But this is nice.
yeah, this is not it. No, it's not. It's not.
You see that things are not connected.
Yeah.
No, because we always work with networks which have a connected component. Well, we always work. It depends. There are networks we have more than one connected component. But what is interesting is to get the largest connected component and to work with this. Even if you work with the largest connected component, you sometimes are able to distinguish different communities there, which are the parts of the system which are more connected between them inside the community than real coordinate. And this is the angular coordinate.
So these angular and the mass is the radius.
Yes, the mass or the popularity is the radius.
But what is the mass for the airport data? What is, you do need two things, right? Mass and some kind of a distance to arrive at this.
So when you do the inverse mapping, this is when you take the topology of the network, which is this is connected to this, then you do this inference technique, yeah, that reverses the model. Let's say you try to apply maximum likelihood techniques to find the coordinates that best reproduce the structure that
you fit the mass of the.
Of course.
Okay, sorry.
Is there a unique solution? Like, is there a unique map outside of a given network when we do the maximum likelihood?
The fluctuation of the values is very small in general.
But so there is a unique maximum.
But
also
there is not
optimal.
there is not a peak. You don't stay here like a peak.
No, I understand, but there is a unique
But
optimal
yes,
capacity.
yes, they can fluctuate a little bit.
So given a network, you have a unique map as soon as you fix one point.
Yes.
The question that in a different way formulated is about like, what does this distance from the center actually represent functionally? I mean, does it have a functional interpretation? I see here two bananas that are basically at the same distance from the center, and then I think like, okay, apparently doesn't really this mass doesn't really have any importance at all.
Yes, but the idea is you have the mass and the angular position.
Elusive trait of an airport. It doesn't represent the number of connections or whether it's a hub.
Yeah, it does. So at this kappa at the end is very much directly related with the degree of the airport. Yeah, this kappa at the end gives you the degree.
But
Yeah.
we expect to see, for example, a place like Atlanta
In the middle, yeah.
in the middle. I mean, Panama, Atlanta.
Why is that in the middle?
Should be in the middle because they have by far the highest degree of connectivity.
Yeah.
No, but it's not that much as, I mean, you were expecting that here, right?
Yeah. Or
In
this,
this data set,
Abu Dhabi or whatever.
no, but in
I mean,
this data set, it's not there, it's here.
But it depends how you normalize it. If you normalize, yeah, I mean, it just depends.
Yeah.
It's just
Because if you put all the flights in the world, maybe the weight cannot be very high, even if you connect to the whole world.
Yeah, that's,
I mean, there is no airport connected to the whole world.
it's
Yeah,
also a
yeah,
log
yeah.
scale probably, so that means that even if Atlanta would have 10 times more than a number two, then it's still on log scale, it's not.
Yeah,
Yeah, and look, this is radial, this is a logarithmic transformation of the
Yeah.
mass. You
Well,
know,
once
so
we are-
you have to consider it.
having the colors, there's a small stripe that is isolated. Which color is that one?
This color is North America, I think this is kind of Alaska, this part. But I mean, this is just one example. What I wanted to tell you is that the embeddings are meaningful, are able to recover information that is not directly explicitly contained there, yes.
Yes, but then I still have a question. Can you clarify? So in
He
one
was frozen.
case, you set up the mass is a proxy of the degree. So the degree of
The mass is the
airport.
proxy of the degree.
But then I look at the picture and as he said, this is just two banana, so which means that the distribution of the mass is very highly concentrated. And the degree distribution we know is very like scalar free. So how I can reconcile these two facts? One banana fact and one like.
What do you say,
scalar free?
Mama? Wait a second. So,
No, by banana, I mean the distribution is very concentrated.
look, the banana is like this and like this. This is angular. The banana is angular.
No, but the
No?
radius, the
The
radius
radius,
is
the
more or less
radius
the
is like
same.
this, okay,
Yeah.
so this we have the distribution of the degrees, yes. But this is radius, which is a logarithmic transformation of the degrees. This is this transformation of the degrees. This transformation of the degrees.
No.
So at the end, the degrees mimic quite well. So if you look,
It's working. Yeah.
No, the chat.
look,
Slides were,
Somebody asked a
Yeah.
question in the chat.
this is
yeah.
another
Videos
example.
frozen.
This is a brain connector. This is another example. This is a brain connector.
She didn't swing
Okay.
the lights for.
And this is a validation of the embedding.
Slides were.
Here you can see different colors at the different hemispheres. Different colors at different hemispheres. So here you can see how well is the embedding reproducing the degree distribution. This is complementary cumulative degree distribution, original, the dots, and the later.
Oh, no, you can start. I think it was the
Start.
camera, the video.
And as compared to the inverted one, which is the Latent, super good, right? I mean, and all the properties, two-point correlations, clustering, and so on and so forth, and probability of connection. They're a little bit more shaky, but it's still good enough. So we do this kind of validation. It's not just that we look at colors. You see, we check that we are reproducing well the properties of the original network there. It was just an example. Because now we go to the point that we wanted to discuss today, right?
Yeah.
How do we renormalize complex networks? But before, you needed to know about this. Yes.
So it's not entirely clear to me, so here the mapping to S1 is meaningful, but if you have some general network about which there's you don't know what the correct mapping is, right? Well, I mean, how do you validate this, or do you see what I mean? You could, like you said, you could also map to S2 and maybe get some different.
Yeah, so to understand about the dimension, we do a few tests. One test is how well we recognize communities there, if it's easier or not to recognize in dimension 1 or in dimension 2 and so on. Another one is to navigate the network. Because when we navigate the network with greedy routing, we are like, it's not exactly the same, but greedy routing paths in the maps that we get are close to shortest paths. Okay, so if the dimension is more right, then this navigation is easier, let's say. So to check the dimension, we also see this, how well we can navigate the network. So the right dimension gives you a better navigation. But this is navigating is that you have a source node, you want to reach a target node, and then you go, you follow a path based on the distances in the underlying space. You go to your neighbor, which is closer to destination, and from the neighbor, again, the same operation. Yeah, and if the embedding is good, that means that you will reach the destination in just a few hops, following links. But okay, I cannot explain.
Finding the shortest path. It's latent space.
I mean, the geodesic in the metric space is close to the shortest path. A good embedding gives you this property. Yes. That's why we use navigability to try to find, for instance, which is the right dimension. But this is a different kind of topic. For the moment, we'll stay with dimension 1, huh? Because otherwise we complicate things. And now we are prepared to try to understand what we did to renormalize networks.
Can you press box so we can read?
Sorry?
Can you press the blue box so we can?
Yes, sure.
Thanks.
Oh, sorry.
So what we do is the following. So we take inspiration in this block spin model, right? In the block spin model by Serrano. We take inspiration, because it's different. Here, what I was saying before, you don't care about renormalizing the space. This box or the 4 go into one box, and this will scale into this box, but Euclidean spaces are similar to itself, so we don't have to care too much. In network, we have to care about how do we renormalize the structure before thinking about processes or dynamics or anything, because of the small world property and so on. So what we did is the following. You take a network and we model the network with the S1 or H2, whatever. That means that we can do the embedding. We have embedding, we have this kind of map. This is S1, doesn't matter if you use H2. Yeah? We have this map. In this map, we make blocks, we constrain by merging nodes which are close in this circle.
But closer in the same angular distance or in the
No, close. So for instance, you can take pairs of nodes, pairs of consecutive nodes. Doesn't matter if they are connected or not. Maybe they are not connected, doesn't matter. Huh? I make box by taking pairs of boxes of size 4 nodes or size 8 nodes, whatever.
With a hyperbolic distance.
No, with the similarity distance, with the distance in the circle that we call similarity distance. With the similarity distance.
Okay.
Okay, not the hyperbolic distance, but the similarity. That's why I'm using the S1 representation. Okay, so you can take pairs, blah, 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 but you don't care that much here. It's not necessary that you care about the distance. So you take neighbors, let's say neighbors in this similarity space, and you make boxes. Then every box is going to be into a constrained supernode here in the new layer. This 2 into this 2 into this, and so on and so forth. And then here you connect 2 supernodes, this one and this one, whenever there were connections between the nodes inside in the previous layer. So since these 2 were connected to these 2, the supernode representing this one and the supernode representing this one are going to be connected in the new layer. Very easy operation, right?
And what happened with the things in between?
Hmm?
What happened with the 2 nodes in between?
These are merged into a single node.
Yeah, no, but I mean exactly in your L0 plane. Between the 2 supernodes, there is a cluster of 2 nodes.
Well, these 2 go into another one. This one goes into this one, and these 2 go into this one, and these 2 into this one. Every pair goes into a new supernode.
More, what's the rule for the connection during the decimation? Because, okay, in your case, maybe there's connectivity between 2.
Inside, if there is inside, you don't care. You are in the new layer, you only care about connectivity between supernodes there.
So, but you basically accept that if the mother node, the parent node connects with the other parent node, you put the connection. Not matter if it's one.
For the moment, one connection without weights. If there were like 2 connections here, I don't care. I just put one connection. Okay, no weights here. I just connect them.
And the only criteria is that the parent nodes have to have connections
in the previous
in the
layer.
previous layer.
That's all.
Okay.
It's very.
How do you decide which nodes to cluster? I mean, here they are nicely spaced out over the surface, so it's very visually clear.
Don't care. You don't care. You just put together every 2. You decide this number. How many?
I can decide on choosing other pairings, and that's perfectly fine.
It's perfectly fine. The only thing is that they need to be consecutive. So it's very important to preserve the ordering of nodes in the circle. So we merge these 2 guys, and these 2 guys, and these 2 guys, because we preserve the ordering of nodes. I cannot merge these 2 with this one here. No, this is forbidden. The ordering of nodes carries a lot of information about the network, so this is very important to keep the same ordering.
Like you define this similarity distance in the circle, and you merge the neighbors that are close to each other.
Yes, and you can make groups of, for instance, I can make this group 2 and this group 3 and this group 2 again. It doesn't matter. As far as I preserve the ordering in the circle, it doesn't matter.
So what if an appropriate embedding was in S2 or S3, you wouldn't be able to do something?
I don't know how, I didn't think about how to do it in more dimensions, how to discourse graining. This is next step.
But you can make also a hypersphere, like a ball.
Yes,
Yeah,
you can make a ball, but then
Yeah.
things are a little bit more intricate, right? Because to make the push graining, but I mean, I have to think. We didn't think yet about this. For the moment, we did it for S1 of this circle, and that's so the procedure is very easy and has a semi-group property. You can go from here to here by making groups of 2 from here to here, or directly from here to here by making groups of 4, and it's the same. Yeah. So it has this kind of semi-group property, and working with the model, you can do it up to infinity, but working with real networks, at some point you have to stop because real networks are finite, and typically you stop at log when your layer has size log n, with n is the original number of nodes in your network. At some point you have to stop. You start having finite effects and so on and so forth. And okay, so very easy. Now it's easy.
Combining two neighboring nodes. So the first step, it's not unique, right?
No, you
And
can.
so if you go from top to the bottom, the possibilities actually multiply. You have at least 3 or 4 non-unique.
Yeah, depending on this number, you have more or less, but statistically speaking, the results are similar. We check. And statistically speaking, the results are similar. What is very
But I'm curious about the semi-group structure because of this non-uniqueness.
What I can say is that we check this, the semi-group structure and everything, just like instead of starting merging here, you can start merging here, this will be this and so on. And even changing this number, instead of 2, take 4, and the results are always consistent.
But then you have to start at the same, start with the same node in the top, basically, to combine.
Yeah, I mean, you can only start in one node at the top. You cannot start here and here at the same time. But it's not that critical. I mean, for convenience, we use the same the same size of the nodes for one layer, but it's not necessary. You can have a mixing of R2 and R4, but then of course, you know.
You need your
battery is running out.
Now the battery. Okay, wait a second.
No, I have the laptop is staggering. Yeah. But like, if you make the appropriate choice, your fixed point should be relatively stable. So you.
Wow, now we have a problem because the only two that work are these two.
Oh, I can put a microphone in mind then.
Okay.
Because this is the one for the microphone. So then. Okay. Yeah. Then I will turn on my camera. Yeah, and you have to mute yourself, and I unmute.
Wait a second.
Oh yeah, you should mute and make volume 0. Yeah, now it's
Everything is muted.
Good? Oh, no, no good. Okay.
There's this echo.
Help?
Are you
You should unmute.
Now?
You have to select the audio. Yeah.
Now they can see.
Okay, now
I'm going
it,
to show you.
but now you should not have your audio. I don't know how to.
It's not there.
The audio.
It's not there. So I don't know why.
Arrow there. Arrow next to the audio.
Which one?
Yeah, this,
Yeah.
and then
Then leave.
leave audio and leave computer audio. Okay,
It's not okay?
yeah, thanks.
Thank you. Thank you very much.
Expert help. Yeah.
Okay, so we apply this. And, that's not working.
Oh, you have to click on that.
No,
This one.
that's weird.
Now, thank you. When we apply this method to real networks, this is what we get. This is what we get. So what I'm showing here are different real networks, internet protocol, music, and there are more. These are not the only ones, these are just examples. Here you have the degree distribution, number of neighbors per node. Here you have clustering coefficient, so the number of triangles for every class of degree K. And these are two-point correlations, whatever. Okay, but this is clustering, basically triangles spectrum as a function of the degree of the nodes, the distribution. When we scale by the average degree of the layer. So what we find in real networks is that when we go from one layer to the next, the average degree grows. The average degree grows. Now, if we rescale the degrees by the average degree in the layer, this is what we obtain. For the internet, we were able to make 5 layers, 2 layers, and so on and so forth. So what do you see here? And this is for communities. Huh?
Sorry, so these figures are already scaled with the average degree?
Yes.
Of the layer?
Of the layer. Huh? But when you rescale by the average degree of the layer, these topological properties of the networks collapse. We observe such similarity, right?
Yeah, but you lose the right-hand tail.
I lose what?
The red dots don't extend to the right.
No, of course, because you have less nodes, so the cutoffs
Yeah, but you have already rescaled that. Did I understand correctly?
We rescale by the average degree, not by the maximum degree. We rescale by the average degree in each layer. The average and the cutoff are different things. Yeah, and we rescale by the average, not by the cutoff. Yeah, that's why this is like shortened somehow. Yeah, but all the curves collapse. So we find some similarity that at the statistical level, all the layers look the same, except for the fact that the average degree grows. The average degree grows, the layers are more dense. So I zoom out on the structure of the network, and I see the same kind of network, statistically speaking, it's the same. The only thing that is a little bit more connected on average. Okay? This is interesting because why should real networks be like this? But they are.
This is because of the rule you choose. So if the node before cross-graining are connected, then the super node are connected. So
Yes.
This is the consequence of the rule, no?
This is a consequence of how you connect the nodes in the neo layer and of how you constrain the nodes. You know, if you constrain the nodes in some other random way, you don't get this. So you need to have the embedding with this similarity distance to constrain in that way and to connect in that way, and then you get this.
But is there any property that is robust related to your choice? Because if you think that a mood scale property when you cross grain many times, maybe an exponent or something would be independent of the choice you make.
I mean, if you renormalize in a different way, typically it's easy to get that the degree distribution scales, so similarity to the distribution, but you don't get the scaling of the clustering coefficient, the amount of triangles that you get in every degree class. This property is very difficult to get.
I see. Like, okay, following the analogy with Kadanoff, like no matter the Hamiltonian you had, if it's the same universality class, your renormalization flows goes to the same fixed point.
Yes, I'm going to talk about where we flow. This is a question that we can I mean, this thing that the average degree increases is giving us some ideas of where the flow goes. But for this, I need to go to the model. I'm going to show you this slide about the model that tells you where the flow is going in networks.
So you claim this is a property of real world networks?
Yes.
If I take arbitrary network and I do the same trick, it doesn't work.
No. So the thing is, you can take the Erdős-Rényi network and you can do an embedding, but it's not going to be meaningful, right? Because Erdős-Rényi networks in the thermodynamic limit have no clustering, right? So in finite networks made of the finite realizations made of the Erdős-Rényi, you will measure some clustering because of finite effects. But in the thermodynamic limit, that network has no clustering, so it's not this category of networks. It's not a complex network.
Yeah. So that means that if I give you a whole bunch of networks, some artificial, some real, you would say I can at point accuracy say which one are real and which one are fake.
So it depends, because if you mimic very well the structure of real networks, I would not going to be able to tell you.
No,
So,
okay, yeah, sure.
It depends on the model that you use. So if you use the S1 network to produce synthetic networks, and then you apply renormalization, you will get something like this for sure. This is very consistent.
So
Yeah.
you don't have a counterexample of a real world network to this.
Well, I mean, yes, there are real-world networks which are not that nice. For instance, going to the example of the airport network, the airport network has less triangles as expected and more squares than expected. Okay? That network has less triangles and more squares. Maybe it's because of business. I have no idea. So in that case, the beta here controls triangles and also controls other cycles, like the squares and so on. But somehow the distribution between how many triangles, how many squares, and so on is anomalous. And in that case, maybe the model is not that good, and then in that case, maybe this is not that clear. Yes. Yes, there are networks for which this is not that clear.
One other question in the analogy again with Kadanoff, like as far as I understood, the renormalization group was invented to explain self-similarity near a critical point of phase transition, because this was not known, and then the relations between those exponents were not explained, and then the renormalization group was created to invent that. But in most approaches in networks, the output is self-similarity in its own. So can you add to this?
For this, we need to go to the model.
Okay.
But before we go to the model, let me tell, yes, because then you will understand why I'm talking just about the structure. But before we go into this, let me show you, because this is the key point of the question. We can reproduce those statistical properties so well, and with the similarity of the statistical properties so well, because the empirical probability of connection that I showed you here as a function of the rescale distance. So remember, this is a kind of rescale distance when I take into account the masses. The probability of connection empirical that I measure in the networks as a function of this has this behavior. Okay? That's why we can reproduce all of the properties, the similarity in the statistical properties of the real networks. Yeah? And when you go to the model that we are using to mimic the networks, what happens is that we prove that the model is renormalizable. What does it mean? That if we transform the masses in this way, this is a beta norm. It's a beta norm. So this is the mass of the supernode as a function of the mass of the nodes in the previous layer. This is a beta norm, but that doesn't matter. Huh? And this transformation of the angle. So the transformation of the angle, you can do it in different ways. The only important thing is that the supernode has a position within the sector that define the nodes in the previous layer. So this is not, but this one is important. If you transform the coordinates in this way, the probability of connection of the model stays the same.
Ah,
The probability of connection of the model stays the same. The distribution of hidden degrees stays the same with the same gamma, except for this region. This is a connectivity phase diagram as a function of beta controlling clustering and gamma controlling the degree distribution.
so sorry, what you say is that in your harmonization procedure, no matter the layer you are in the decimation, they have the same generative probability.
Yes, belong to the same, we say belong to the same ensemble. The networks that we get at every layer belong to the same ensemble. The only thing that changes is the average degree. So the parameter that the radius changes in the model because the number of nodes is different, and the parameter that controls the average degree is rescaling in this way.
And
that's why the average degree changes. But beta that controls clustering remains the same. The degree distribution remains the same with the same gamma, except for a region where you have gamma above 3. In this region, then you start losing the similarity of the degree distribution. But if you have networks with this beta and this gamma, all of this region is the similarity region of the connectivity phase.
One more question, maybe not in the implementation, but whether do you think this makes sense for a real-world network? Or because you could say, okay, the one scale can see the neighbor scale that can see the other neighbor scale, and not that the micro scale propagates to all scales with the same, just replicating the same probability. Or you...
I mean, this is a property of the model, right? And this is for the time being, this is the best model that I know to replicate this similarity that we measure in real networks.
I see. Okay.
These are properties of the model, right? But this property mimics, reproduces, helps us to explain this similarity that we observe in real systems. So if you have a network that is well described with this beta and this gamma in this region, for instance, the internet is here. If we adjust our model to the internet, we get a beta is about 1.5 and this gamma 2.1 more or less here. If you are in this region, colored blue, of the phase space, then and look like renormalization, according to our model, you flow towards a fully connected graph. The average degree increases, and if we were able to keep it at infinity, then you will flow until a fully connected graph. If you are in this other region, we have no networks here, right? But if you were able to have a network here, this network will flow towards a one-dimensional ring. Yeah. So this is telling us about the transition between a small wall and non-small wall networks. Yeah. So this transition that we can study by applying renormalization and flow and so on is the transition between a small wall and non-small. So this is structural. I'm not saying anything about dynamics or anything. So this is one step before the processes, but this is needed here because the renormalization of a space is not trivial anymore in networks. Yeah, and so we needed this transformation that keeps the same properties of the space. You see, of the structure of networks, because for physical space it's trivial, for networks it's not. You know, so how we have to do this transformation? This is one way in which it works. Now, from here we can start thinking about what happens with dynamical processes and so on, you know? Huh?
So
this is the kind
a
of thing.
little bit, can you say something about the region 3 there? Because the fact that there is such a sharp transition between, okay, this is renormalizable and the other one not.
Well, yeah, this is you do the mathematics with the model, and this is what we observe. There is this kind of region, this condition here, in which we start to see that there's a similarity of the distribution is not there anymore. So if you have a network,
and your gamma was it's related to the probability of connection, right?
Yes. Well, gamma is related to the degrees distribution of degrees, to the degree distribution of masses.
Did you see? Oh, okay.
Yeah. So, for instance, the brain is in this region.
Well,
The brain is in this region, but it seems to be like here, but the brain is in this region.
Yeah.
But it also depends on beta. Not all the networks which are in this region are in 3. But yes, we have in the phase space, we have this region in which, so this is basically for scale-free networks, that we say scale-free networks, networks where the gamma is between 2 and 3, let's say. It's more clear for, we can be more sure that they are there. Okay?
When you say the brain, you mean which network?
Connectome. The connectome.
And has how many nodes in this case? Because it's not so.
Let me show you, because.
What is the dashed line through the?
Sorry?
What is the line, dashed line through the?
This line?
Yeah.
Yeah, this line separates 2 different regions in which the exponent of the way in which the average degree grows changes. So you see, this is the way in which the average degree grows from layer to layer. Depends on R, is the size of the box, and this exponent that depends on the properties of the network. So in this region, this exponent has this form here depending on gamma. We call it the gamma dominated region. While in here, this exponent has this form. This is the beta dominated region. These are from calculations in our model. But in any case, grows. In all this blue area, it grows, but in different ways, on different properties of the system. It comes out from the analytic calculation, with approximations, of course. We cannot do it exactly.
And if I understand correctly, the flows towards means basically having subsequent transformations.
Yes, yes. In the model, because in a real network, you stop before here, before this point. But in the model, you can go up to infinity, and if you go up and so on, then you will get the fully connected system. Yeah. Yeah. But in real networks, of course, at some point we have to stop.
Yeah. Do you think then, because for me, let's say what can be a difference that in your model, the probability is preserved across every decimation,
yes.
And in normalization is not obvious because you get a new Hamiltonian and you don't know exactly it has the same type of interaction that the previous one. Do you think that the fact that you have to converge to a fully connected graph, then the inherited probability makes this to happen the whole in all layers?
I don't know, because so look, one of the basic properties of networks for us is that they are sparse. So that means that at some point you cross to the dense regime, and the dense regime changes everything. So I really don't know where it can happen. This is what the theory tells us, but regarding real networks, I really don't know. Because then you have this complication that you go from the sparse regime to the dense regime, and for networks which are dense, the picture is different. So this is theoretical for the model and so on. Okay, let me, as you were asking about the brain, let me tell you about it. I don't know how much time I have.
We already -30, might have. That is fine. No, the food is there, so we just.
I think food is a slide.
It's fine.
So up to this point, I was showing you networks, and then we applied the renormalization, and then we saw that the layers were so similar, but we started with single snapshots, right? And you say, okay, that's why it's okay. So that means that the model is a good model to reproduce the structure of the network. And okay, this is also similarity that we uncover with the model, but at the end we have to apply renormalization to uncover the similarity. Okay, can we find some other more stringent proof?
Well, before you talk about normalization in the human connectome, when you apply your hyperbolic map, can you get the brain subnetworks already spread in the hyperbolic space?
Yes.
Oh, cool. Okay. Nice.
Yes,
Yeah,
yes,
okay.
we have a mapping. So this is something that we say. So the geometry of the brain connectome is hyperbolic. It's not Euclidean, because this kind of models explain better the connectomics of the brain between regions at the level of connections between regions. because we don't have data to go. Now Drosophila has data. We will check, but we will see. So we were able to find a data. Well, we did a collaboration with Patrick Hartmann and Serrano in Switzerland. They had these reconstructions of brains of individuals at 5 different layers. For every individual, they had the connectome of that person at the resolution of 1,000 nodes, the same brain at a different resolution with 500 nodes, and so on and so forth. This is for each person. Okay, they have this kind of reconstruction, and they knew the hierarchical correspondence between the layers. So they knew these 2 regions here correspond to this region there, and so on and so forth. So they did this from the anatomical point of view, nothing related with our model. So they did this kind of multi-scale reconstruction of human brain connectors based on anatomical information. Okay, and they have those data sets there for 84 persons into different kind of techniques that they use to get the data. Well, this data is from them, these 14-year-old people, and then we also use a different data set coming from the Human Connector Project just to double check that the results were okay. Yeah. So we end up with like 80 people, 80 brains at 5 different kind of resolutions. And we said, okay, let's try to see if our model is good with this, no? That we already have the multi-scale reconstruction, and let's see if it's good, and it is. Here you see the comparison of what we measure in every layer of the multi-scale brain, the anatomical reconstructions, and what we measure in the geometric renormalization flow when we apply our model and the renormalization technique to the higher resolution layer. So we apply the embedding of this layer here, and we do geometric renormalization, we produce these layers here, and then we isolate, and then we compare like this, right? And then everything collapses.
One question, is this a average connectome or you did this per person?
No, it's person, like individuals.
And how do the scaling change per person? Or they have all the same scaling or?
They are very similar. Our brains are all very similar at this level. You know, at this level of analysis, with statistical level of analysis, we are all very similar. We didn't see difference between male and female. We checked no differences. This is very coarse grain, right? This is the brain represented in 1,000 regions to the last one is, I don't remember, so maybe 100 regions. So it's very coarse grain and no differences.
Do you know how they got like anatomical networks based on the, like, did they have like fMRI data? Like, how did they reconstruct networks? Because originally the data is not a network.
They did fMRI and tractography.
Yeah, tractography can be a network.
The 2 things together. They did the 2 things together. So in one way they defined the regions, and in another way they were tracking the fibers that were connecting the 2. So these are an anatomical reconstruction of brains. So axons going from one region to another. And so it's very nice, for me it's very nice. So we measure, I don't know, degree distribution, class coefficient, blah, 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 to correlation, fixed graph, whatever, and all the curves collage. That means that our model is geometric renormalization is nice to reproduce this multi-scale.
Each layer has same number of nodes.
Sorry?
Like, how do you compare the 2 layers? Like each layer has.
This is the same layer here and here, right?
And the subsequent layers you keep show.
This is roughly half the number of nodes here, roughly half the number of nodes, and we applied size 2 for the boxes. That's all. Without adjusting much to the exact number or anything, because we are working at the statistical level. So at the statistical level, you don't need much to go define tuning, you know.
And the graphs at the bottom are scaled again by the average connection?
Yes, always. Always. Just here. Yeah. Yeah. So this is nice. Just to finish, this technique, there is no the inverse of the renormalization process, right? But we were able to work out an inverse method to grow networks in a similar way. So now we know how to do this renormalization process, but we also know how to grow networks using a kind of using an inverse, the renormalization method, to grow networks in a similar way, because we know there are real networks which grow in this way, which grow in a similar way. You know, so now we have this methodology that allows us to zoom out and to grow networks in this similar way. So now we are prepared to start thinking about processes, I think.
Can I ask you about it? Because here the underlying network has a geometric space connected to it, right?
Mhm.
So a key geometric distance. Did you check whether your distance on in the S1 model actually corresponds with what is the geometric distance between the brain cells?
We did it, and it's not actually the same. It's not actually the same. And when we use that distance, the anatomical distance, in our model, for instance, to connect regions, we are not able to reproduce that well the topological properties of the connector. That means that that distance is not the only factor that affects connections in the brain, the formation of connections in the brain. We have one paper, and there is some evidence also in this paper here.
Yeah, but sorry, but how do you mean like we don't reproduce that well? Because you know you have many more free parameters if you fix the distance already. Oh, sorry, the other way around. If you have fewer parameters to act, you do a maximum likelihood estimation, and I think that if you already fix the distance between the different points on your S1 model, you actually have fewer free parameters, so you automatically will have a worse fit.
Yes. But that means that that distance that you inferred, right?
Yeah.
If you see that this distance that you inferred is not the distance that you measure in anatomical terms, that means there is something else that explains connectivity in the brain. Yeah. So I don't know, yes, maybe it's not the only reason why things are connecting there. Yeah, typically it's not. Typically, what we find is that it explains a lot. So this physical distance in these complex systems explains a lot, 80% maybe, but the rest, the 20% that remains, you need something else. And then this kind of representation in the hyperbolic or S1, doesn't matter, somehow is like inferring what is missing there.
But here, the left graph is actually what you say the anatomical graph, right?
Yes.
So how did you define that, or how did you choose for your different points there, the distance and the radius, and the location? Because you know, it looks very similar, but that is maybe due to the fact that how you draw it.
Well, I mean, when you go here, yes, forget about the drawing. So when you go here to the empirical data and you measure these properties, which are topological, nothing to do with the picture, which are topological, you see some similarity. You just forget about everything that I talked today. You take this data, you measure the topological properties, the distribution, and you observe that they collapse. So this is there in the brains. This belongs to the brains. This is a similarity. Now, our claim is that with these models and this renormalization procedure, we are able to reproduce this similarity that we observe in the empirical brains.
But in a way, you making the same hyperbolic mapping with the real data. That's, let's say, the figure in the left.
No, you don't need to do it here. It's just a representation. If you want to compare, because here we did it because we wanted also to compare the geometric communities. But it's not necessary. I mean, for the distribution, for the things that I'm showing you here, forget about this. For all these things, you don't need to do any embedding here. You just measure on the topology of the network.
This is only to get the communities in the hyperbolic.
Yes,
Okay.
last here. because once you have the embedding, you can measure whether nodes concentrate in a specific sector. This defines geometric communities. And then you can check whether these are consistent with the ones here and so on. Yeah. So I think I arrived, a very long talk. Thank you very much for listening. Just let me acknowledge my collaborators in all those papers, because this is work that we developed in a few different papers. So Professor Mariangeles, we are running the lab together. We did all the theoretical part is together. And then Dr. Huasen, who was a postdoc, now is a professor in China. And our PhD student now a super businessman in quantum computing. So and the data of the brain was from Patrick Hartman and Jessel. Okay, thank you very much.